Swayam Prabha. Digital India. Educated India.
Today we are going to discuss about abrasive water jet machining process, that is also known as abrasive water jet cutting process. The organization of the today's lecture is as follows: introduction, working principle of abrasive water jet machining process, what are the various elements of abrasive water jet machining system. Then we will move to the parametric analysis, then some visualizations and how this abrasive water jet is moving within the workpiece will be shown. Then finally, the applications and conclusions will be discussed. Let us see abrasive water jet machining setup. In introduction, first before we really go for working principle of abrasive water jet machining, let us see some of the peculiar applications of this abrasive water jet cutting process. And here I am trying to show you various processes which are based on abrasives, or where you are using the applications of abrasives in cutting or machining processes. On the left hand side, you can see that there are the traditional processes which are based on the application of abrasives. They are grinding, honing, lapping, super finishing and similar other processes. One of the point to note over here is that all these processes are applicable for electrically conducting as well as electrically non-conducting materials, and the advanced machining processes which are based on the application of abrasives include abrasive jet machining, which we have discussed already. Here there is a carrier medium which is carrying the or moving the abrasive particles is the air, which is easily available, cheap and not toxic. So, that is preferred over here. Here the air driven abrasive jet, when it is used in AJM process, the material removal rate is comparatively low, accuracy is not very good and efficiency of machining of AJM process is also low. There are various avenues of improving this abrasive jet machining process that we will discuss in the next slide. On the other hand, if you see ultrasonic machining process, which is also based on the application of abrasives in cutting or machining of various advanced engineering materials. Here the carrier medium is liquid and abrasives are mixed in the liquid, say normally water, and that water mixed with abrasives is known as slurry, and the tool in case of ultrasonic machining is vibrating at ultrasonic frequency. This process also gives material removal rate comparatively low, efficiency is also low. Some improvements have been made in this particular process to develop new processes, specifically the processes which are used for finishing purposes, that I will show you in the next slide. As you can see on the left hand side, the improvement on the abrasive jet machining process is the result, or as a result of the improvement we have what is known as abrasive water jet machining process, which has many advantages compared to specifically abrasive jet machining process. There is no dust in the environment, whatever material removal is there, abrasive particles are there, all of them are within the water. So, environment pollution is minimized. Compared to AGM, it has very high cutting speed. There are no thermal stresses developed in the machined workpiece, because first thing is the whole workpiece is completely in contact with the water throughout the machining process. Also the forces are comparatively in a localized area. There is no delamination when you are machining the composite materials. glass fiber reinforced plastic is one of the example. There are no fire hazards, low level of power requirement and quality of the cut edges is comparatively better. On the other hand, as an improvement over the ultrasonic machining process principle, we can say that we are having a process called as abrasive flow finishing process, which is using viscoelastic material as the medium in which abrasive particles are added. This viscoelastic material acts as a self deformable stone, which we will discuss later on in other chapter. Now, in this particular case, there are no ultrasonic vibration as we have in ultrasonic machining. It uses normally hydraulic power unit for applying the force. Sometimes we can also use pneumatic power for giving the sufficient force for the movement of the piston, so that it pushes the medium inside the working zone. Let us understand the working principle of abrasive water jet machining. It should be water jet machining, not C. As you can see here, this is the schematic diagram of abrasive water jet cutting system. You can see there is a high power water tube through which the water at very high pressure is supplied, and then on this side we have the abrasive port through which abrasive particles are supplied. These abrasive particles may be alumina, Al2O3, silicon carbide or some other abrasive particles. Then there is a orifice through which the water jet is coming out at a very high velocity. As we will see, the velocity of the water jet can be as high as 800 to 900 meter per second, depending upon what pressure is used. Then you have a mixing tube over here. In this tube you can see clearly that abrasive jet is mixed with the water jet and both form abrasive water jet. Now, while coming out of the mixing tube, we have here the abrasive water jet, and the velocity of this abrasive water jet is very high, and with such a high velocity, when it hits the workpiece over here, the kinetic energy of the abrasive particle is responsible for removal of the material from the workpiece, and we can calculate the kinetic energy of individual particle by the formula half m v square, where m is the mass of the particle and v is the velocity with which it is hitting the workpiece. Now, when it hits the workpiece, it is not necessary all the time that it is hitting at a normal or at a 90 degree angle to the workpiece. As you can see on the right hand side, the abrasive particle is hitting the workpiece and it is moving at an angle other than the 90 degree to the workpiece surface. Now, there are two types of the forces that are acting over here, as you can see, Fx and Fy. Now, here force Fy is responsible for penetration, that is acting in this particular direction. So, it is responsible for penetrating inside the workpiece surface, and Fx is responsible for removal of material in the form of the chip due to the shearing action. As you can see over here, this is the Fx force that is acting over there, and there is a reaction force that you can see over here. When it penetrates inside the workpiece surface, there is always a resistance from the workpiece surface for penetration, and that is the reaction force. Now, this particular figures and some of the descriptions in this chapter have been taken from the paper written by Hashish Muhammad, a modeling study of metal cutting with abrasive water jets. It was published in Journal of Engineering Materials and Technology, Transaction ASME, January 1984, volume 106, pages are 88 to 100. Now, when the abrasive jet or abrasive water jet has penetrated inside the workpiece surface, how or in what direction this jet is moving? As it enters inside the workpiece surface, as you can see, it is following a curved surface, and if you see a particular particle, now it has two velocities. One is the velocity in the x direction, another is the velocity in the y direction or h direction, and these are the components of the velocity v, that is the resultant velocity. And as I will show you in the next slide, that the surface that you are getting after machining is not really a smooth surface, rather it is a serrated surface, as you will see in the next slide. Now, here this indicates the surface which has been cut over there. So, you can see these are the boundaries of the jet which it is moving along the particular path, which you cannot predict easily. However, models have been developed to predict this particular path. Now, what happens really when it starts from one edge to another edge, as you can see over here, at the entry it cuts it and then it starts exiting from the outside or least resistance path, and then you can see in the beginning after entry stage it starts tilting or bending at a particular angle, and striations in the surface are created, as you can clearly see, and whenever there is a blind cavity, this kind of the bottom surface is obtained, and it is not acceptable in most of the applications. So, for through cutting it is a comparatively better process than for blind cutting. Now, as jet is moving, you can see the striations are also being formed at the exit also. This is more or less the same way as at the entry, and you can see again the striations on the side of the exit of the jet, again taken from the same paper. So, this is really the kind of the surface that you are going to get, cut surface that you are going to get from the abrasive water jet cutting process. Now, you can see these are the striations and these are the kind of the marks that will be seen on the cut wall of the workpiece, which you have obtained by abrasive water jet cutting, and this is the kind of the generated surface that you are going to obtain. Now, mixing of water jet and stream of abrasive takes place in the mixing tube, as we have seen in the earlier slide. Rapid rise in abrasive velocity occurs in the mixing tube after it is coming from the port, abrasive particles coming from the port and mixing with the water jet, they come out of the mixing tube. When impingement of an abrasive on the work material takes place, momentum transfer occurs, and that is given by half mv square. This leads to removal of material by erosion, shear or brittle fracture. It depends upon what are the properties of the workpiece material. If it is a brittle material, then fracture may take place. If it is a ductile material, then deformation, erosion and shearing are going to take place. Pressure is normally 400 megapascal, and the jet speed, maximum jet speed that you can obtain normally people have worked with is 900 meter per second, which is very high. Cutting in upper part of the curve takes place due to the mechanism that is known as erosive action, and then cutting in the lower part of the curve take place due to the deformation. Now, this is the actual abrasive water jet cutting machine which IIT Kanpur purchased. Now, the details of this particular machine can be seen on this site, which is given over here. Here you can see the video also for this particular machine. Now, you can see the various parts over there. This is the CNC control panel, with the help of which you can feed different parameters, you can control various movements of the jet. Here this is the enlarged view of the jet, you can clearly see the abrasive water jet visible over here, and this is the cut part of the workpiece that you can see here. This is the cut part of the workpiece. Now, here is the abrasive tank in which you fill that dry dehumidified abrasive particles, and this is the water reservoir where whole of this tank is filled with water, and here you will keep the workpiece, as I will show you in the next slide. Now, you can clearly see various other elements of the abrasive water jet cutting machine, Now, this is the abrasive tank which is having dry dehumidified abrasive particles. Now, here is the nozzle and it is going to cut the workpiece over there, and you can see this is the water tank, and this here you are going to place the workpiece somewhere here. Now, you can clearly see these are the workpieces which are being machined, not very clear, but here is the area where machining is going to take place. So, these are the different views of the abrasive water jet cutting machine. This we have already seen. The important thing that you can see here once again is that the distance between the bottom of the nozzle and the top surface of the workpiece, that is known as nozzle tip distance, or it is also called as stand off distance. Now, it is used to machine metals as well as non-metals. Non-metals materials are like ceramics, composites, rocks, etc. Metals you can machine copper, aluminum, tungsten carbide, lead, or even superalloys can be cut by this. Various kind of operations can be performed like drilling, cutting, deburring, etc. It can cut any kind of material with reasonably good edge quality, acceptable important applications of this abrasive water jet cutting is that you can use the robot, and it can be used for dismantling of nuclear power plants with the help of a robot. This is very important application, because in nuclear power plant human beings are not permitted to go there because of the radiation effect. So, for such kind of applications where you can control the cutting operation with the help of the robot at remote places. Let us see what are the various elements of abrasive water jet machining system. First one is the pumping system, another is the abrasive feed system, water jet, nozzle and pressure of the water as high as 415 megapascal or so, for which the motor of around 75 horsepower is used. It gives the high velocity jet. Another is the abrasive feed system. We have seen in the figure of the system, abrasive water jet cutting system. It delivers dry abrasive particles to control the flow rate of dry abrasive particles, control the orifice diameter and suction pressure in mixing tube. You can change the orifice diameter. It cannot supply abrasives over long distances, otherwise the kinetic energy or the velocity will slow down. So, what researchers have proposed, or they are doing the experiments by using directly slurry to feed over a long distance. They take the slurry over a long distance and then they directly feed the slurry over there, and however, it will require more power than the present systems. Water jet nozzle diameter normally varies between 75 to 635 micrometer. Now, abrasive jet nozzles, there are various functions of the nozzle in abrasive water jet machining. First one is mixing of abrasive and water jet, as we have seen, and then forming high velocity jet. Materials of the nozzle are tungsten carbide, boron, carbide, sapphire, or very hard materials and resistant for wear materials can be used for this purpose. For high life of nozzle, normally sapphire material is used, but it is more expensive than other materials listed over here. Now, there are various kind of abrasive jet nozzles or abrasive water jet nozzles. Now, first one is the single jet side feed nozzle. It is simple to make, but it rapid wear of exit part of the nozzle takes place. It gives non-optimal efficiency of mixing of water and abrasives, as we will see in the figure. Now, as you see in this particular figure, abrasive is coming from this port as well as this port, and water is coming from the central port, and both of them are mixing somewhere here. Now, after mixing they are going out, and since you can see on the outer side abrasive particles are there and in the middle side water jet is there. So, abrasive particles are coming directly in contact with the nozzle surface, inner surface of the nozzle. So, wear of the nozzle will be more, and you can see the distance between the bottom face of the nozzle and upper face of the workpiece is the nozzle tip distance, and when this abrasive water jet hits to the workpiece surface, the removal of the material takes place. Here one point is to be noted, that this stand off distance is not fixed always. When the jet is moving inside and it has moved sufficiently below the workpiece, and here is the say nozzle, this is the nozzle, then the stand off distance will be this one, not this one. So, it has to be, this is the SOD, no, and so this has to be measured from the bottom face of the nozzle and the top surface of the workpiece where it is removing the material. This point should be carefully noted. Another one is known as annular jet central feed nozzle. It gives better mixing of water and abrasive, but in this particular case mixing is outside the nozzle. It is less accurate or it gives less accurate machining as compared to the earlier one. In this particular case cuts or the kerf width is higher compared to the earlier one. As you can see here clearly that water is coming from the sides and abrasive is coming from the central port. Now, both of them are mixing here outside the nozzle, and you can see the divergence taking over there, and because of this divergence of the jet, abrasive water jet, the accuracy of the cutting reduces compared to the earlier type of the nozzle. Now, because of this is less accurate. It is surrounded by multiple water jets in a converging annulus. It gives higher nozzle life and better mixing. This is very important. I will just explain it with the help of the figure. Now, it is difficult to make and costly to fabricate. Now, in this particular case, as you can see, it gives a higher nozzle life and better mixing. If you see this particular figure, here water is in contact with the sides of the nozzle or inner surface of the nozzle, not the abrasive particles are not directly in contact with the inner surface of the nozzle. That is why the life of the nozzle is higher compared to other types of the nozzles, and mixing is also inside the nozzle and it gives a better mixing compared to other nozzles. As you can see here, nozzle tip distance is shown over there, and water is coming from this, from the annular side, from all around it, and that is why it is known as multiple jet central feed nozzle. Types of catchers. Now, if you see here, the abrasive water jet is coming at a very high velocity. After cutting the workpiece, if it hits the table on which you are going to machine the workpiece, then it will penetrate inside the table also, and it will damage the table immediately. That is why what is done is that before it really hits the table or the container or the tank of the water base, the velocity of the abrasive water jet is reduced to the minimum possible value, so that the impact with which it hits the table or the bottom of the water tank is low enough not to damage it. That is why the catchers are being used. So, catcher is used to minimize the velocity of the abrasive water jet before it hits the base of the water tank, so that the tank does not get damaged. Now, you can see here, this is the nozzle and abrasive water jet is coming out of it, it is cutting the workpiece. Then there is a tube. In this tube you have the two types, you have the obstructions on all around it, and when this water is coming inside this, it hits these obstructions over here and its velocity reduces continuously before it is really out from the tube, and this obstruction are there to reduce the jet energy. Here in this particular case, nozzle is stationary and workpiece is moving. So, that is shown, movement of the workpiece is shown here, and nozzle is stationary. Now, in the second type of the catcher, nozzle is moving, but workpiece is stationary. A water filled settling tank underneath the workpiece is there. It minimizes abrasive water jet velocity by hitting stationary water filled in the tank. To collect remains of abrasive water jet, the tank filled with water is used. For this purpose, you can use for movement of the water, you can use the flexible hose if pressure is less than 24 megapascal. You can use the rigid tubing if pressure is greater than 24 megapascal. Now, here you can see clearly, this is the nozzle and the jet is through cutting, the water jet is coming in the abrasive water jet is coming in the water tank, and this is the tank filled with the water, and abrasive and water jet, when they hit the water stationary in the tank, their velocity reduces considerably before it reaches to the bottom of the tank. Let us have some parametric analysis of the abrasive water jet machining process. Before we discuss it, let us first see what are the various parameters involved in abrasive water jet cutting process. Now, first of all, water is there, the pressure of the water and the flow rate of the water, both are the parameters for this particular process. Then there is a water nozzle, material of the water nozzle is important, as we have already seen, and the cross section of the water nozzle, it can have a circular cross section, it can have a rectangular cross section also. Then the hardness of the workpiece is very important parameter, other material properties are also equally important. Then the workpiece, whether it is brittle or ductile, that will decide the material removal rate and the mechanism of material removal rate also. Then you have the abrasive particles, size of the abrasive particles, what is the absolute size or mesh size of the abrasive particles is important, whether they are coarse or they are fine, and type of the abrasive, whether it is silicon carbide, alumina or other type of the abrasives. Then flow rate of the abrasive is another important parameter. Then abrasive feed nozzle, what is the cross section of the abrasive feed nozzle and the material of the feed nozzle, because it is not very hard, then the nozzle itself will wear out slowly and the feed, you cannot control accurately the abrasive feed. Then there are the cutting parameters like feed rate, number of passes, angle of cutting and stand off distance. These are the cutting parameters which affect the performance of the abrasive water jet cutting process. And then the mixing tube, diameter of the mixing tube and the length of the mixing tube, both are important cutting parameters. The output responses which are normally measured and based on which the performance of the abrasive water jet machining process is evaluated are the machining rate, quality of the cut edges, kerf quality and depth of cut. Let us see again the same thing, water we have seen flow rate and pressure, abrasive type, size and flow rate, water and abrasive jet nozzle material and design. Cutting parameters are feed rate and stand off distance, workpiece material, mixing tube, angle of cutting, traverse speed and number of passes. These three are very important. Now, what angle the jet is hitting the workpiece surface? This is the workpiece surface, and what angle the jet is hitting, that will decide the mode of removal of material, and it is very important. So, this angle is important, which it is making theta, with reference to the surface of the workpiece. Now, traverse speed is another very important parameter. This, as I will show you in the next slide, is the relative movement or relative velocity between the workpiece surface and the abrasive water jet, and number of passes, as we already know, say in case of traditional machining processes, say turning, if the thickness of the material to be removed is much larger, then not in one pass, rather in many passes. Same way, if the thickness of the workpiece to be cut over here is very large, then in place of single pass you can use multiple passes for cutting the through cutting of the whole workpiece. Now, let us see the effect of pressure on the depth of cut. As you can see in this particular figure, there is here is a point which is written as critical pressure. This is the minimum pressure or minimum kinetic has got certain strength, and unless the kinetic energy of the abrasive particle crosses that, it cannot penetrate inside the workpiece surface. That is why you can see there is no cutting in this particular zone, that is the before the critical pressure is reached, and as the pressure is increasing, the depth of cut is also increasing, but beyond a certain pressure, this is not a linear relationship, this is a non-linear relationship, and it tries to stabilize beyond a certain pressure. Now, also if you see here, as the abrasive flow rate increases, the depth of cut is also increases, but again this is also not a linear relationship. So, you can see here that minimum pressure or critical pressure or kinetic energy of abrasive particles needed to cut a material is there, and it is different for different workpiece materials. Same thing is shown over here with the various experimental points. As the pressure is increasing, the depth of cut is also increasing, and as the abrasive flow rate increasing, the depth of cut is also increasing. So, the same thing is given here as the explanation that below the critical pressure no cutting is taking place, different for different workpiece material, it depends on workpiece properties. Above definite jet pressure, machine depth tends to stabilize. Relationship with machine depth is steeper with higher abrasive flow rate. Increased pressure will lead to higher cost of pump maintenance, because if the pressure is very high, then the maintenance of the pump becomes more expensive because of more wear and tear. It gives lower efficiency at very high pressure. Higher nozzle wear rate is also observed with very high pressure. Below the critical pressure, the stresses developed in the workpiece are lower than the yield stress. That is why you do not get any removal of the material. Here it shows the effect of the water jet pressure on the depth of cut. It initially increases and afterwards it tries to stabilize it. Now, you can also see that this is the nozzle diameter D1 and D2. Now, if nozzle diameter is larger, then the depth of cut also decreases. As you can see over here, it is because if the same power is there, then the pressure of the water or abrasive water jet coming out is smaller, and that is why the depth of cut is also smaller. Water flow rate. Water is the propelling fluid that enables high abrasive flow rate, and the flow rate you can have is as high as 5 kg per minute. Abrasive velocity normally is 300 meter per second. Abrasive water jet are coherent, hence more suitable for cutting, and these are much more coherent as compared to the abrasive jet machining process. Now, here you can see here the water flow rate is directly proportional to the under root of the pressure P, and it is directly proportional to the square of the diameter of the nozzle, that is d n square. Machine depth is proportional to the velocity of the abrasive particles as well as the mass flow rate of the abrasive particle that we can see here. above the critical value of the mass flow rate of the abrasive particles, the depth of cut starts reducing. Increase in mass flow rate leads to the wear of mixing nozzle, higher wear of the mixing nozzle and reduced efficiency, mixing efficiency. That is why there is always an appropriate or critical mixing critical amount or critical value of the mass flow rate of the abrasive particle. Selection of the type of the abrasive, cost of abrasive, it depends, selection of the type of the abrasive depends on the cost of the abrasive, nozzle wear rate, environment considerations and machining rate, and finally it also affects it is also affected by the particle strength. Let us see the effect of abrasive flow rate. Now, as we can see here, as the abrasive flow rate is increasing, the depth of cut is increasing in different kind of the abrasives, glass bead is there, silica sand, granite sand or alumina. Now, one thing we can see here, that depending upon the type of the abrasives, the depth of cut is different in different cases. Now, abrasive particle size, there is always an optimal particle size for a particular application, which includes the workpiece material also. Fine abrasive particles are good for shallow depth of cut and coarse abrasive particles are good for high depth of cut. Different abrasive sizes for different depth of cut are also proposed by some of the researchers. However, in practice it seems to be a little difficult task. Now, abrasive materials, the machine depth is function of the type of the abrasive also. Now, traverse speed is the relative motion between abrasive water jet and workpiece. It can be achieved by moving abrasive water jet or by workpiece. If we see the relationship between traverse speed or traverse rate and depth of cut, this is the kind of the relationship that we obtain, that as the traverse rate increases, the depth of cut decreases. If you see here, as the traverse rate is increasing, the area generation rate is increasing and there is the optimum area generation, and beyond the base it start decreasing. Now, depth of cut decreases with an increase in the traverse rate, which may be within 10 millimeter per second. Now, let us understand this, what is the traverse rate. Suppose this is the abrasive water jet and this is the workpiece. To cut the whole length of the workpiece, either the workpiece can be moved in this direction, then the jet, abrasive water jet will remain stationary, or if the workpiece is kept stationary and then the jet can move along the surface of the workpiece. So, the relative motion between the abrasive water jet and the workpiece decides what is going to be the total depth of cut in a given time, because suppose we are considering this particular area, then depending upon for how long the jet is here, it will keep penetrating. If it is for very long, it will keep penetrating deeper and deeper. If it is for a very short period, then it may penetrate only up to this length and go out. So, the traverse rate is very important in deciding the depth of penetration or machine depth. Another thing is, when you are cutting this, say if you take the top view of this particular workpiece, it is cutting like this. Now, if you see this area which has been cut over here, now I take the cut area from here, say suppose it has been cut in two pieces, then one of the surfaces that has been created will be like this. So, whatever is this area of the cut surface, because similarly there will be, this is, say this is cut surface of this part A, similar cut surface will be for part B. So, whatever is this area generated and this area divided by the time taken, that will be called as area generation rate. So, you can see here that the area generation rate in terms of millimeter square per second, this particular relationship is followed. So, this is the area generation and the traverse rate that we have just seen. Overcut decreases with an increase in traverse rate. If this traverse rate is increasing with an increase in traverse rate, if this traverse rate is increasing, that means the jet is moving very fast. So, this is the kerf width. Now, when this is the kerf width, I remake it here and suppose this is the size of the jet. Then if I take the enlarged view of this, then it becomes like this, and this is the jet size. Then whatever is this difference, that is known as overcut. Or if you want to take, say, you can call it as radial overcut. If you want to take diametral overcut, then this plus this so twice the